All right, suppose we have two functions, f and g, and they're just minding their own functionally business. And let's suppose we choose two x values, an a and a b. And suppose we're interested in the exact area bounded by the curves f and g and the lines x equal a and x equal b. All right, so what we're going to do is work out this area using an integral. All right, so how are we going to use an integral here? Well, remember, an integral is just an adding machine. All it does is it adds up lots of little things and gives you something meaningful out of it. So to get this area, what we're going to do is add up a whole bunch of little rectangles. And in order to do that, we're going to set up one rectangle and kind of get at the heart of how to find the area of that one rectangle. And then we're going to just use an integral to add up a whole bunch of those rectangles. Now, I've drawn a rectangle here, but let's try to imagine that it's infinitesimally thin. All right, in fact, the actual thickness of this rectangle we're going to call dx, which you want to think of it as tiny change in x. So we're going to regard one rectangle as a tiny amount of area. So let's just call that dA. Now, what's the equation for actually evaluating that tiny area? Well, it would be the height of the rectangle, let's call it h, times the width of the rectangle, which is dx. All right, but what is h? The height of that rectangle is just the upper function minus the lower function. So that would be f of x minus g of x. So that is our formula for tiny bit of a. So you want to think of this tiny bit of area as just the height of the rectangle times the width of the rectangle, which is infinitesimal, right? It's dx. Okay, great. Well, how do we use that to find the area of the entire region that we're interested from a to b? Well, that's where an integral comes in handy, okay? An integral is just an adding machine. So the area of the region is just the sum of the dAs. Well, what are the dAs? That's the sum of the upper function minus the lower function dx. So where does it start? At x equal a and x equal b. Remember, the bounds of integration must match the variable of integration. All right, so that's it. We're going to go into some examples now, but really it's just a matter of setting up an integral with the upper function minus the lower function, starting at your left endpoint and ending at your right endpoint. Okay, so here we're going to sketch a region which will enclose an area, and then we're going to use an integral to find that exact area. So let's start by sketching the curves that are given here. All right, so y equal 2 to the x. That's an exponential curve. And then the line y equals 6, that is a horizontal line. And the line x equals 0, that's a vertical line coinciding with the y-axis, which means that the region we're interested in is that guy right there. Okay, so we have a clear sense of an upper function and a lower function, and a left end of this and a right end of this. Now the right end is not clear what that is yet. So the first thing we should do is figure out that right-hand endpoint. So what do we know about that endpoint? Well, we know that that is the x value for which 2 to the x is equal to 6. So we're going to solve 2 to the x equals 6. Okay, so take the ln of both sides. We can bring that x down in front. And we get that x is ln of 6 divided by ln of 2. So now we can conclude that the area, which is the integral from a to b of the upper function minus the lower function, is equal to the integral from the first x value, which is 0, to the last x value, which is ln of 6 over ln of 2, of the upper function, which is 6, minus the lower function, which is 2 to the x, dx. All right, now that is the setup of this area problem. Now, it's entirely possible that on a quiz or an exam, you'll be asked simply to only set up the problem. Or you may be asked to set up and find the area. In this case, we had to find the whole area, so we need to actually work out the integral. But if it were a setup only problem, that's where we would stop. Okay, so pay attention to exactly what's being asked in a question. And this integral itself isn't too hard because we know the antiderivative of both of those terms. So we can just say that this is equal to antiderivative of 6, which is 6x, minus the antiderivative of 2 to the x, which is 2 to the x over ln of 2, the lower bound being 0 and the upper bound being ln of 6 divided by ln of 2. All right, so let's plug in the upper bound. We have 6 times ln 6 over ln 2 minus 2 to the ln 6 over ln 2, and that's all over ln 2. And we're going to subtract the antiderivative with 0 plugged in for x. So that would be 6 times 0 minus 2 to the 0 over ln 2. And wow, we certainly have our work cut out for us here. Let's put our attention on this part right here, 2 to the ln 6 over ln 2. Well, what is that? Well, there's several ways we could work this out. We could see that this is equal to 2 raised to the log base 2 of 6 using the change of base formula. And the 2 raised to the log 2 of stuff will just equal the stuff. So we can see that that evaluates simply to 6. All right, so what do we have here? We have 6 ln 6 over ln 2 minus 6 over ln 2 and plus 1 over ln 2. So this looks like 6 ln 6 minus 5 all over ln 2. And that is our final answer. So it's very nice that we can find the area of an exquisitely defined shape like that using calculus and obtain a very interesting answer in terms of logarithms like we have here. Of course, if you wanted a numeric answer, you would just reach for your calculator and there you'd get a decimal number. But in this course, this is the format we want for our answers. Okay, here we are with the same type of problem. So we're going to sketch these two sine curves. Now we are only interested in the region from 0 to pi. So let's start with the first sine curve. Let's just call this 1 here. So we know that sine of x from 0 to pi just kind of makes a shape like that. And we know sine of 2x has a period of pi, right? It'll be 2 pi divided by the coefficient 2, so that's a period of pi. So we have an entire phase of sine 2x between 0 and pi here. All right, and we are interested in the region between these curves. So that would be this little piece right here and this bigger piece over here. All right, so yeah, we want to find the area of that. Who wouldn't want to do that? So, well, the first thing we should notice is that this area, this region, is split into 2 smaller regions. And that presents a little bit of an issue because for the region on the left, let's call this A1, and let's call the region on the right A2. So for A1, the upper function is sine of 2x and the lower function is sine of x. But for A2, the role of upper and lower function has switched, right? For A2, sine of x is the upper function and sine of 2x is the lower function, which means we're going to have to do this in 2 separate integrals, and we'll just add our answers. So we're going to work out A1, and then we'll work out A2, and we'll add the total. All right. This also means we're going to need to figure out where they intersect. So they intersect somewhere between 0 and pi over 2. So to do that, we're going to solve sine of x equals sine of 2x. Okay, and we'll just reach for our pre-calculus skills here, or trigonometry skills. So in order to solve this equation, we're going to have to find a way to get all the trig functions involved to the same argument. So right now they have 2 arguments. There's an x and there's a 2x. So if you know an identity, then this is fairly straightforward, because the right-hand side is 2 sine x cosine x. So now all the trig functions have the same argument, which is just x, which means we can do whatever we need algebraically to solve this. And what I'm going to do is move everything to one side of the equation. And now we can factor sine out. And this equation splits into 2 separate equations. So we have sine of x equals 0 and 2 cosine of x minus 1 equals 0. Now remember, we're working in the interval from 0 to pi, so we don't have to go and root out all the infinitude of solutions to this. We just need to find what appears to be the first positive solution to this between 0 and pi. So sine of x equals 0 produces 0 and pi as solutions. Okay. Over here, what we have is cosine of x equal 1/2. So that produces a solution of pi over 3. Comparing these answers with our graph, you can see, well, they would intersect there at 0. They would intersect here at pi. That's the 0 and the pi, which means this guy right here must be the pi over 3, and that's the number we've been after here. Okay, so the area, which is A1 plus A2, is the first area, which is A1, is the integral from 0 to pi over 3 of the upper function, and the upper function in that little region, remember, is the sine of 2x, and the lower function is sine of x. So upper function minus lower function plus the integral from pi over 3 to pi of, and now we're talking about the second region, that bigger one, where the upper and the lower function were reversed. So this would be sine of x minus sine of 2x. So there's our a1, and there's our a2. All right, now there are several ways we can proceed here. One is you can just kind of keep working this out line by line, but if you'll notice, these two integrals are very similar to each other. We unfortunately cannot easily combine them to a single integral because they're not actually the same integrand. However, I think it would be a good idea to work out as side work this integral. Sine of 2x minus sine of x, just as an indefinite integral. Okay, then once we've worked out the general antiderivative, we can return to the main thread of the problem. And a1, we can see, is just that antiderivative, but with the bounds 0 to pi over 3 plugged in. And a2 is actually the negation of that antiderivative with the bounds pi over 3 to pi in, right? So we're only going to do kind of the calculus once here. So now let's work out this side work, and we should probably do this as two separate integrals because this first one is going to require a u substitution and the second one will not. So it's better to split them into two little integrals like this. And for this guy, we're going to quickly let u equal 2x. So du equals 2 dx. And that converts this first integral into sine of u times du over 2. And the second integral here, the antiderivative of sine is negative cosine of x. And let's get our constant. Okay. This first integral evaluates to negative 1/2 cosine of u, and we have plus a cosine of x, plus our constant. And reverse substituting, we know that this is negative 1/2 of cosine of 2x plus cosine of x plus c. So our side work conclusion is that the general antiderivative of sine of 2x minus sine of x is exactly what we have there. Negative 1/2 cosine of 2x plus cosine of x plus c. Okay, and we're going to use this fact. Let's start by working out a1. So if you recall, a1 was the first region, and that was 0 to pi over 3 of the upper function, which is sine of 2x minus sine of x dx. Okay, well, we've already done the legwork here, working out this antiderivative. So we know that that's just negative 1/2 cosine of 2x plus cosine of x with the bound 0 to pi over 3. So this is negative 1/2 cosine of 2 pi over 3 plus cosine of pi over 3 minus, let's plug 0 in, negative 1/2 cosine of 2 times 0 plus cosine of 0. Okay, so we have negative 1/2 and cosine of 2 pi over 3. Well, that's second quadrant, so this will come out negative. So it'll be negative 1/2. Cosine of pi over 3 is positive 1/2. Okay, cosine of 0 is 1, so we have a negative 1/2 there. And cosine of 0 is 1. There we are. So we'll just add up this mess of things. Looks like 1/4 plus 1 minus 1. So 1/4. Okay, let's work out a2 now. So a2 was pi over 3 to pi of sine of x minus sine of 2x dx. And if we want to take advantage of our side work, we'll just throw a negative in front of this. And swap the order of the terms. Okay, so that's equal to negative of the antiderivative. We worked this out as negative 1/2 cosine of 2x plus cosine of x with our bounds pi over 3 to pi. All right, very good. So why don't we distribute that negative back in before we start plugging in the bounds? Otherwise, I'm worried we might just get inundated with negatives. So let's go to positive 1/2 cosine of 2x minus cosine of x from pi over 3 to pi. And now we'll plug our bounds in. So we'll plug pi in here. We get 1/2 cosine of 2 pi minus cosine of pi. And now we'll plug pi over 3 in. 1/2 cosine of 2 times pi over 3 minus cosine of pi over 3. Okay, well, cosine of 2 pi is positive 1, so this is 1/2 minus cosine of pi is negative 1. Cosine of 2 pi over 3 is negative 1/2. And cosine of pi over 3 is positive 1/2. Oh, great, we still ended up with a huge mess of negatives. We have 1/2 plus 1 minus, plus 1/4 plus 1/2. So this would be 2 plus 1/4, so that's 9/4. All right. So we're almost done this monster. We have our A1, which was 1/4. We have our A2, which is 9/4. And now we can conclude that the area is the sum of those two pieces. So that would be 1/4 plus 9/4, which is 10/4. That reduces to 5/2. So the combined area of that blue region has exactly an area of 5/2. I find it especially striking that such an intricately defined region can have such a simple area as 5/2. Okay, let's graph it. All right, y equals the square root of x. Well, that basically looks like this. It's the top half of a horizontally oriented parabola. And y equals x minus 2. That is just a diagonal line shifted down a couple units. The region we are talking about is only within the first quadrant. So we're not going to include this piece, which is in the fourth quadrant. We are only after that piece right there. Okay, so we have a clear upper function, and we have a very clear beginning and ending, sort of a left and a right of this thing, although we would need to figure out that point right there. However, we do not have a consistent lower function here. Okay, in fact, right at this point, we also need to figure out, because if you look at the left side of this thing, let's call this A1. So A1 has a consistent left, a consistent right, a consistent top, and a consistent bottom. And A2, same thing, consistent top, consistent bottom, consistent left, and consistent right. So we actually have to work this out in two separate integrals. All right, so let's start by finding this guy right here. That is just the intersection point of the two curves that were given. Okay, so we would have x minus 2 is equal to the square root of x. And if we square both sides, then foiling the left, we would get x squared minus 4x plus 4. Squaring the right, we get an x. So this becomes x squared minus 5x plus 4, little quadratic factors. So we get x minus 4, x minus 1, and we get solutions of x equal 4 and x equal 1. Now I'm going to argue that x equal 4 is the one we want, and we're going to throw away x equal 1. Okay, so x equal 1 is what would happen if we continued the parabola, and that's an x equal 1 right here. Now the equation that we solved doesn't know the context, so it's just going to give us that x equal 1, which we will reject. But it also gave us the x equal 4, which we can put in right there. Okay, what about that other point? Well, we can see that that point is the x value where the line y equals x minus 2 has a y value of 0. So to find this point, y equal x minus 2 and the horizontal line y equals 0 intersect, we're just going to set 0 equal to x minus 2, and okay, so our area is A1 plus A2, and we can see that A1 is the integral from 0 to 2 of the upper function, which is the square root of x, minus the lower function, which is the line y equals 0. And we're going to add to that the integral from 2 to 4, upper function, which is the square root of x, minus the lower function, which is x minus 2. So there's our setup, and all we have to do is actually work out those integrals now. So we can do a little bit of cleanup here before we get into the calculus. Let's write this as rad x dx plus 2 to 4, and we have rad x minus x plus 2 dx. Okay, so the antiderivative of x to the 1/2 is x to the 3/2 divided by 3/2. So I'm going to just start writing that as 2/3 x to the 3/2, or x rad x even sometimes. Again, 2/3 x to the 3/2 minus 1/2 x squared plus 2x. Okay, you may have wanted just to work out A1 independently and then A2 independently, but here I don't feel like it's going to be a huge problem doing it the way we're doing it, just kind of all at once, one line at a time. So let's plug 2 in, and we have 2/3 times 2 to the 3/2. Let's write that as 2 rad 2. Minus, we'll plug 0 in, and I love plugging 0 into integrals like this, because that's just going to be 0. Plus, now we'll take this guy and plug 4 in. So we have 2/3 times 4 to the 3/2. That's the square root of 4, and then cubed, so that would be 8. Minus 1/2 of 4 squared. 4 squared is 16, so half of that is 8. Plus 2 times 4, which is 8. And then we are subtracting what we get here plugging 2 in. So 2/3, 2 to the 3/2, I'll write that as 2 root 2, minus 1/2 of 2 squared, which actually just comes out to 2, and then plus 2 times 2, which is 4. Okay. So 2 is 6/3, so this would be 16 minus 6 in the numerator, which is 10/3. Final answer. So this thing has an area of exactly 10/3. All right, let's talk about an issue with the last example that we just did. We actually worked it out in a pretty inefficient way. So the reason we did that inefficiently is because we were forcing ourselves to integrate with respect to x, which is really the only way we've talked about. So integrating with respect to x means that we were adding up little rectangles of a differential width dx, right? So we added up little rectangles that looked like this, and then over here, little rectangles that look like this. However, we had to split this into 2 regions and integrate from 0 to 2 and then from 2 to 4. What if instead of forcing ourselves to integrate with respect to x, we allowed ourselves to integrate with respect to y, which means we would have like a horizontally oriented rectangle. Okay, it would have a little width here of dy, or you can think of it as a little height. Okay, and now to get the horizontal length of this rectangle, we would simply take, say, the rightmost function and subtract the leftmost function, and that would give us the horizontal length of this rectangle. Remember, this is an infinitesimally narrow rectangle, so those little corner pieces aren't actually visible. If we were to approach this problem that way, then we wouldn't have had to do this in 2 integrals, because we have a consistent rightmost function, we have a consistent leftmost function. Okay, integrating with respect to y, we would have had y lower bound and y upper bound. Our lower bound would have been y equals 0, and our upper bound would have been whatever that number is, which we could easily find. As it turns out, that number is just 2. So here, we would integrate from 0 to 2, kind of the rightmost function minus the leftmost function dy. Okay, and that would work out to whatever the right answer is. We got 10/3 when we did it earlier. Okay, so we are going to redo this example the better way, but first, let's just quickly establish this principle in general. All right, let's say we have 2 functions and they're just minding their own functionally business, but this time x is regarded as a function of y. Let's call this guy x equal g of y, and we'll call this guy x equal f of y. And this time we're going to choose 2 y values, so why don't we have, say, y equals c, y equal d, and that is the area that we're interested in. So what we're going to do is add up a bunch of rectangles that look like this. They have a width of dy, so we're going to integrate with respect to y. And this dimension of the rectangle is just the rightmost function minus the leftmost function. So the area of that very infinitesimally thin rectangle is given by the rightmost function minus the leftmost function times dy. Okay, I mean, think of this just as, like, say, x2 minus x1, which is going to give a horizontal x length. And x2 is given by f of y, and x1 is given by g of y. And that horizontal distance between them is x2 minus x1. So there's our dA, and the area of the entire region is just the sum of the dAs. So that would be the integral from c to d of f of y, the rightmost function, minus g of y, the leftmost function, dy. Okay, so let's go and redo that last example. Okay, I hope that you can look at this thing, first of all, and agree that it really is a lot easier to integrate this with respect to y, right? We have that consistent beginning, we have that consistent ending right here. Those are the two y values. We have a consistent right-hand curve and a consistent left-hand curve. So our first job here is to write the curves as functions of y. So for the equation y equals the square root of x, we're just going to solve for x, and we get that x is equal to y squared. And for the equation y equal x minus 2, we will solve for x, and we'll get x equal y plus 2. Looking at our graph from earlier analysis, we do know this is the point 4, 2. Well, we figured out that that's x equal 4, and of course if you just plug it into either of these two equations, you'll get that that's a y value of 2. Which means that our integral is going to run from 0 to 2. So our setup here is 0 to 2, rightmost function minus leftmost function dy. So that 0 to 2, the rightmost function here we can see is the line, which is given by x equal y plus 2. And the leftmost function we can see as the parabola, which is given by x equal y squared. Again, if this were a setup-only problem, which you may encounter on exams, that would be where we'd stop. This is a find the area all the way down, which we expect to get 10/3, because that's what we got when we worked it out the inefficient way earlier. So applying the fundamental theorem of calculus, we can replace the integral with its antiderivative. And let's plug these numbers in. Notice that if we plug 0 in, all the terms there are going to be 0. So that's cool. So with a common denominator of 3, we have 18 over 3 minus 8 over 3, which is 10 over 3. And that does comport with our earlier answer. So life is awesome.
Yes.
All right. I hope you can take a look at this particular region and very clearly see that integrating with respect to y is vastly superior to integrating with respect to x, which means that a sample rectangle will look like this. It will have width dy, and its length will simply be right curve minus left curve. And for the entire region here, we have the same right curve and the same left curve the whole time. In fact, all we have to do is figure out what these two y values are. Well, the first one here at the bottom is certainly 0, so we just need to figure out what that second one is. And that's the upper bound of our integral. Okay, so we're just going to do this by setting the two equations equal to each other. Moving all the terms to the right, we have 2y squared minus 6y. And we can factor 2y. So we get a solution of y equals 0 and a solution of y equals 3. Looking at our graph, yes, there's our 0 and there's our 3. So we'll see that we integrate y equals 0 to y equals 3, right function minus left function, dy, and we're good to go. Okay, let's take a quick look to see which one our right function is. Our right function appears to be the 2y minus y squared, and the left function is the y squared minus 4y. Distributing the negative and combining like terms, we get 6y minus 2y squared. Six y integrates to 3y squared minus 2/3 y cubed from 0 to 3. So we'll plug 3 in. 3 times 3 squared is 27. Okay, 3 cubed is 27, over 3 is 9, 2 times 9 is 18. And we'll plug 0 in. And we get an area of 9.